Look around you. A bottle, a food wrapper, a cardboard box, a takeaway container, a shopping bag, a delivery package. Packaging is everywhere. But here is the surprising question. What happens to all of it after we use it? For a few minutes of convenience, some packaging materials can remain in the environment for decades or even much longer. And this creates a major sustainability challenge. But there is an important scientific misconception we need to address. The solution is not simply to replace every plastic package with paper. It is not simply to choose something labeled biodegradable, and it is not simply to recycle more. Sustainable packaging is much more complicated. To understand it, we need to look at the entire life cycle of packaging, from raw materials, manufacturing, and transportation, to use, collection, recycling, reuse, and final disposal. So what would truly sustainable packaging look like? Let's explore the science. What is packaging actually designed to do? Before discussing sustainability, we need to understand why packaging exists. Packaging protects products. It prevents contamination. It reduces physical damage. It can extend shelf life. It allows products to be transported efficiently. It provides information. And in the case of food, packaging can sometimes prevent spoilage. That means packaging itself is not necessarily the problem. The problem occurs when packaging uses excessive resources, has a short useful life, is difficult to recover, or creates pollution after disposal. This is why the most useful question is not, which material is green? Instead, ask, what packaging system provides the required function with the lowest overall environmental impact? That is a life cycle approach. UNEP emphasizes that plastic pollution needs to be addressed across the entire life cycle of products, from production through use and disposal. Step 1. Reduce unnecessary packaging. The most sustainable package is often the package we never needed to produce. Imagine buying a small product wrapped in plastic, placed inside a cardboard box, surrounded by another plastic layer, and then placed inside a delivery bag. Every additional layer requires material. That material requires resources. Manufacturing requires energy. Transportation requires energy. And eventually, someone has to manage the waste. So the first principle is reduction. Can the package be made smaller? Can unnecessary layers be eliminated? Can a product be sold without an additional outer package? Can the packaging perform several functions at once? Can concentrated products reduce the amount of packaging required? These questions can prevent waste before it is created. UNEP's work on plastics emphasizes reducing problematic and unnecessary plastic use as one of the key steps toward a circular economy. Step 2. Design for reuse. Now imagine two containers. One is used once and thrown away. The other is designed to be washed, refilled, and used dozens of times. The second container may require more material initially, but that does not automatically make it less sustainable. Its environmental performance depends on how many times it is reused, how it is transported, how it is cleaned, and what material it replaces. This is why reuse must be evaluated as a system. A reusable package only provides its full potential when people actually reuse it enough times and when the supporting collection and cleaning infrastructure is efficient. Refill systems can also reduce the need for producing a new package for every purchase. Instead of buying a new container every time, consumers can refill an existing one. This changes the basic relationship between products and packaging. Packaging stops being a disposable object and becomes part of a longer use system. Step 3. Choose materials scientifically. There is no universally perfect packaging material. Plastic, paper, glass, aluminum, and other materials all have different properties. Plastic can be lightweight and durable. Glass can be reused and recycled, but it is relatively heavy. Paper can come from renewable biological resources and is widely collected in many systems, but coatings, adhesives, inks, and contamination can affect recyclability. Aluminum can be recycled repeatedly, but producing primary aluminum requires significant energy. So material selection needs to consider the function of the package. What is it protecting? How much material is required? How far will it travel? How many times can it be reused? Can it be collected? Can it be recycled? And what happens at the end of its life? These are life cycle questions. Step 4. Design for recycling. Here is an important misconception about recycling. A package may technically be recyclable but still not actually be recycled. Why? Because recycling requires an entire system. The package must be collected. It may need to be sorted. It must be compatible with processing equipment. There must be a market for the recycled material. And the economics must make sense. If packaging is made from several materials that are permanently bonded together, separating them can become difficult. If different polymers are mixed, recycling may become more complicated. If food residue contaminates material, it can interfere with processing. This means packaging needs to be designed with the recycling system in mind. UNEP highlights design for circularity, including products that can be reused, recycled, or composted in practice. The phrase "in practice" is extremely important. A package should not simply be recyclable in theory. There needs to be a realistic pathway for it to be recovered and processed. Step 5. Avoid material combinations that create waste. Some modern packages look simple but are actually complex structures. A food pouch, for example, may contain multiple layers that provide strength, moisture resistance, oxygen barriers, and protection from light. These properties can be extremely useful, but when different materials are permanently combined, separating them at the end of their life can become difficult. This creates a design challenge. Packaging engineers need to balance performance during use with recovery after use. The ideal package is therefore not necessarily the simplest-looking package. It is the package that performs its required function while minimizing environmental impacts throughout its life cycle. Step 6. Use recycled materials. Another important strategy is increasing the use of recycled materials. Why? Because recycling can reduce the need for virgin raw materials. Instead of continually extracting new resources, materials can circulate through the economy. This is the basic idea behind a circular economy. UNEP describes circular approaches as systems that prioritize reducing unnecessary products, reuse, and recycling while conserving resources and reducing environmental impacts. But recycled content also has limits. Some materials lose quality during recycling. Some food contact applications require strict safety standards. And recycling systems still need reliable collection and processing. So recycled content is one part of a larger system rather than a magic solution. Step 7. Be careful with biodegradable. Now let's examine one of the most confusing words in sustainable packaging. Biodegradable. A package labeled biodegradable may sound automatically environmentally friendly, but biodegradation depends on conditions: temperature, moisture, microbial activity, oxygen availability, time, and the specific material. Some materials labeled compostable require industrial composting facilities with controlled conditions. If they end up in an ordinary landfill or the natural environment, they may not behave as consumers expect. This is why labels need to be precise. Consumers need to know not only what a material is theoretically capable of doing, but what infrastructure exists to manage it. Step 8. Consider food waste. Here is another surprising part of packaging science. Sometimes using more packaging can reduce environmental impact if it significantly reduces food waste. Food production itself requires land, water, energy, fertilizer, transportation, and labor. If packaging protects food and prevents spoilage, the environmental benefits of avoiding wasted food may outweigh the impacts of the additional packaging. This is why sustainable packaging cannot be judged by material weight alone. A lightweight package that causes food to spoil rapidly may not be the best solution. A slightly more substantial package that greatly extends shelf life may perform better overall. Again, the life cycle matters. Step 9. Improve transportation efficiency. Packaging also interacts with transportation. Imagine two packages containing exactly the same product. One package is large and filled mostly with empty space. The other is compact and efficiently shaped. The compact package may allow more products to fit into a truck, ship, or aircraft. That can reduce the number of journeys required and therefore reduce transportation impacts per product. Packaging design can therefore influence more than waste. It can influence logistics. This is why engineers consider dimensions, weight, stacking, protection, and material efficiency. Step 10. Build a circular packaging system. The ultimate goal is not simply to create better disposable packaging, it is to redesign the system. Imagine a package moving through a circular loop. Materials are extracted. A package is manufactured. It is used. Instead of becoming waste, the package is collected. It is reused or its materials are recovered. Those materials become inputs for new products. The cycle continues. This is fundamentally different from the traditional linear model. Take, make, use, throw away. UNEP's circularity framework emphasizes reducing unnecessary consumption and designing systems for reuse, repair, and recycling. What can consumers do? Consumers do not control the entire packaging system, but purchasing decisions can influence demand. Choose products with minimal unnecessary packaging. Prefer reusable systems when they are practical. Use refill systems where available. Separate recyclable materials correctly according to local rules. Avoid assuming that every package labeled eco-friendly has the same environmental performance. And most importantly, learn to question the entire life cycle. Where did the material come from? How long will the package be used? Can it be reused? Can it actually be recycled where you live? What happens if it cannot be recovered? These questions are much more useful than simply asking whether something looks environmentally friendly. What should the packaging of the future look like? The packaging of the future may not be based on one miracle material. Instead, it will probably involve better design, less unnecessary material, more reuse, better refill systems, materials chosen according to function, designs optimized for recycling, more recycled content, clearer labeling, better collection systems, and stronger producer responsibility. The most sustainable packaging is therefore not necessarily plastic-free. It is not necessarily paper. It is not necessarily biodegradable. It is packaging designed as part of a circular system. Because sustainability begins before the package is manufactured and continues long after the consumer throws it away. The real question is not, can we make packaging disappear? The real question is, can we design packaging so that its materials remain useful instead of becoming waste? That is the challenge of sustainable packaging, and solving it requires science, engineering, policy, business innovation, and smarter choices from all of us.